Organisms are a huge part of the soil. Now, clearly, we think of the big things like earthworms and snails and molds, and they're really important to the soil because one of the things that they do is they burrow and tunnel through the soil. So they aerate the soil and help to make spaces in the soil for air and water to enter. But then we have a lot of smaller organisms, bacteria, fungi, nematodes, mites, and a whole lot of other organisms in there as well. And they feed off the organic material in the soil. That's their habitat. It's also the habitat for the snail. So when we lose soil through erosion, maybe we pave over it for a parking lot or we alter it, then we get rid of the habitat for these organisms. Let's focus a little bit more on the bacteria. This is a great place to tie back in biogeochemical cycles, in particular the nitrogen cycle, because in soil, the bacteria are really the driving force behind a lot of the nitrogen cycle. For example, in the roots of legumes, we have nodules, and inside those nodules are bacteria, nitrogen-fixing bacteria that can turn atmospheric nitrogen into a form that plants can use, like ammonia. But it's not just those nitrogen-fixing bacteria. There's denitrifying bacteria and nitrifying bacteria, and lots of other species of bacteria that live in the soil that drive the nitrogen cycle. So another huge reason why soil is important is this whole process. So erosion can happen naturally through things like wind or water, but there are some things that we do, like tilling a field, that may accelerate the movement of wind and the movement of water. And so as it's moving, it's losing the soil and really affecting that micro ecosystem right there. We can also have sediment pollution in waterways, increasing the turbidity, reducing the ability of photosynthesis to happen, or the soils get clogged in the gills of organisms. So erosion, you need to understand in terms of just what is it and how does it naturally happen by wind and water, but also some of the anthropogenic forces that push more erosion to happen. Okay, so the next picture, is another really big important thing in soil are the roots of trees. So these roots have a really tight grip on soil. So if there is wind or a big flow of water, these roots help to reduce erosion because the soil is grabbed on. And so if we do something like overgraze a plot of land, and we reduce that vegetation, then its roots go away and that area is more prone to erosion. So you can see some different types of root systems here. And in the one on the left, you see those little root nodules that would have nitrogen-fixing bacteria in them. And it's also nice to point out, which is probably not related to the AP exam, that with trees, we can have these huge, vast root systems. And in a lot of our deciduous trees, those root systems are as wide as the crown of the tree, if not wider. And they go down pretty far. So if we're ever transplanting a tree, you can't just trim the roots that you can see right there at the surface. You have to go about 1.5 times the base of the crown in order to get all of the root system, and then down about halfway as tall as the tree is to get a proper root system. So a lot of times they have to do specialized pruning in order to keep those roots back a little bit so that they don't, so that they are able to be transplanted without taking this massive root ball that's the size of the tree. Now, with that in mind, also, when you think of urbanization and we come in and we plant trees that are, 5 years old in these new neighborhoods, they're not going to have the root system that is equivalent to what it should be in nature. So it can cause a lot of times for these neighborhoods that have trees transplanted into them, that they won't have that massive root system that spreads out as wide as the base. So those trees that have been transplanted may fall over more easily than ones that you see out in the woods, which is why if you have big trees on your property that were planted later, then it can be a problem, and other people will, that they might want to chop down the trees and things like that. So back to soils. Here's our soil triangle, and you'll be happy to think that you're probably not going to have to take out a ruler and do any measurements here on the soil triangle. But the composition of soil is important. So we have to look at the physical properties that make up soil. And so first, when we look at the soil triangle, we know that it is sand, silt, and clay, and that all of these are good in a certain proportion, but that our sweet spot really is right here in the middle. We want loam, so we want a good mix of all three. And so why do we want a good mix of all three? Well, for one thing, we have to think about the porosity of the soil, and that is how much space there is in between the particles of soil. So you can have a soil that has no space in between, so it doesn't hold any air or water. You can have some spaces in between, or you can have, like all the way over on the right, we can have soils that have a lot of space in between for water. And that would be a good soil to use for, say, an aquifer, if I'm trying to relate it to something else. Another important factor to think about in soil is permeability. And permeability is the rate at which water can flow through the soil. So if you were to have sand and you had a handful of sand and you poured water through it, that water would just go straight through the sand, right? But if you had that same equivalent amount of clay in your hand and you poured water on it, it might just set on top, and it could sit for months without ever like really seeping through. So, we did some testing in class where we looked at how different the particle sizes were. When we have sand, it is really kind of bigger particles. You can pick them out individually. And then the next one is silt, and it's, a much smaller particle, but not quite as small as clay. Clay is so small that you can't really feel the differences in clay in your hand. But when we rubbed the sand on our hand, you could feel it. It was like rubbing salt. So you could feel it and you could see it, and the particles are visible to the naked eye. But when you get down to clay, you don't really have that. So the reason that we want all three is because if we have a porous soil that has sand in it, then it allows for permeability to occur and water to flow through the soil. But clay is really important because clay helps to really latch on to a lot of nutrients, and it kind of helps, having clay and silt in there helps slow down the permeability so that it takes longer for the water to flow through the soil, and in that process allows for some of the clay to hold on to some of the micronutrients a little longer, which allows plants to uptake them from their roots. If we have all sand, like on a beach, we can't really have very many plants growing there, because the water rushes right through them, and they're not able to intake any soil. But conversely, the opposite being clay, if you have too much clay, then it just sets on the top, and if you keep irrigating, you might even just like waterlog the roots and make the roots rot out. It doesn't really get all the way down to the rest of the roots. So when would this matter? Well, it would matter if you were, say, building a pond for drainage from agriculture for like animal waste, or if you wanted to line a landfill. You wouldn't want to line it with sand, because then when it rained, the water would make all of that waste run right through and into the aquifer. So what they would do is they would line it with clay, and so it's very impermeable, and so it makes it so that you don't have any of those hazardous materials, any of that excess nitrogen and phosphorus from, say, a hog waste farm or something. It doesn't get a chance to leach through because that impermeable layer of clay that's on the bottom. Okay, so by having some of that clay in the soil, you could really get into the chemistry of, cation exchange capacity and things like that. But what we're really getting to is if you go back to that first image, in soils that have a lot of clay, you probably won't have that E horizon because the clay is going to be able to latch on to a lot of those nutrients like calcium and magnesium. So they won't form that alluviated layer with all of the leached out materials in it. So that brings us to when we're talking about different amounts of nutrients in the soil and cation exchange, that is how we're going to measure fertility. And so we did that in our ecosystems, and we also modeled how having layers in the soil help to help filter water. So that's a really amazing ecosystem service that soils provide, is that they help to purify water. It's like having coffee filter on top of coffee filter. So that's another really important thing to think about when we're looking at soils. So the next concept that we're going to look at is watersheds. And so here we see all of the watersheds of North Carolina. And so if you are in Winston-Salem and there is stormwater runoff or some type of construction or agricultural runoff or even just rainwater, it's going to end up flowing down into that Yadkin River basin. It can go through some tributaries, but eventually it'll end up in the Yadkin River, and then it will flow out towards the ocean. So all of the water in that watershed is going to flow towards the same area. And then right where we have Kernersville, we have kind of a divide, and that's what it's called, is a divide. And so after that point, if you go east a little bit, then it's going to flow into tributaries that lead into the Cape Fear Basin. So in North Carolina, we are special because we have so many watersheds. And in the image on the right, you see the Mississippi watershed, which is composed of lots and lots of tributaries that eventually run into the Mississippi River and then out into the Gulf of Mexico. So this is really important when we think about like agricultural runoff and urban sprawl and construction and roads and things, that all of this is going to eventually flow into a watershed.